Okay, so what we want to do is show that the three heights of a triangle always intersect at a single point. And the height of the triangle, as we know, is the line that is perpendicular to one side and passes through the opposite vertex. So this height C is perpendicular to AB and passes through vertex C. And we can see the same for height A, which passes through vertex A and is perpendicular to side CB, and height B, which passes through vertex B and is perpendicular to height A, or is perpendicular to the side AC. So obviously on this triangle, the three heights do intersect at a single point, but we want to show in general that that's true. So we do that by putting the triangle on a coordinate plane, and we're going to give these 3 points some generic coordinates. So obviously A is at the origin, so we're going to call that 0, 0. We're going to put point B at lowercase b, 0. We're going to put point C at lowercase c, d. Now what we want to do is we want to find the equation of the line that we want to find the equation of the three lines and show that these three lines all contain the same point. We're allowed to assume that two of the heights always intersect because we know that two non-parallel lines always intersect, and because a triangle has no parallel sides, obviously lines that are perpendicular to those sides are also not going to be parallel. So I'll start by writing the equation of the line for height C, which is obviously just x equals lowercase c. Here I'll give my capitals an underline to make it clear. And the equation for line A, well, we can do using point slope form. So it passes with the point 0, 0. And the slope of this line is the perpendicular slope of the slope of BC. So the slope of BC is minus d over b minus c. So the perpendicular slope to that is going to be b minus c over d. Great. And then that passes through the point x minus 0. So we see that the equation is simply y equals b minus c over d times x. Okay, so now we want to find the point where these two lines intersect, and we can do that just by plugging in x equals c from this equation into this equation right here. So the intersection point is at y equals b minus c over d times c, or bc minus c squared over d. Okay, great. So now we know that the coordinates of this point are c, and then bc minus c squared over d. Great. Now we want to write the equation for line B, and we want to see if it passes through that point. So the equation for line B, we're going to write it as the same way as we did for line A using point slope form. So it's going to be y minus 0 equals, and then to find the slope of the line, we just take the slope of the side and write the negative reciprocal. So the slope of this side AC is c minus 0 over d minus, or d minus 0 over c minus 0, so d over c. So the slope of the height is going to be minus c over d, and that passes through x minus b. Okay, so we can rewrite this as y equals minus c over d times x minus b. So if we've done everything correctly, if we plug in x equals c, it should pass through this line B. So let's do that. So we have y, or it should pass through this same point, excuse me, c, bc minus c squared over d. So let's plug in x equals c. So we get minus c over d times c minus b, and that is minus c squared minus bc over d, and that is just the same as bc minus c squared over d. So we see that all three lines intersect at the same point. And because I didn't specify any of the coordinates exactly, you could just plug in any numbers for any triangle and this would work. We call this intersection point of the three heights the orthocenter. And it's sometimes also known as the center of gravity or center of mass. Because if you were to cut this triangle out on a piece of paper and balance it at on a pencil tip exactly at that point, it would balance perfectly. We know that this proof is the most general because even if we have a triangle maybe that looks like this, it doesn't seem to fall on any horizontal and vertical axis, well, we can just redefine our coordinates along a single side, say, like so. And obviously by rotating the frame, we get the same picture above here. So I'm going to show the proof one other way, which is a geometric proof that does not require any algebra. And this is an interesting proof because it's the same way the ancient Greeks like Euclid might have done this proof. So let's go to a new page and let's draw our triangle. Okay. And before we do this proof, we need to define a few things. So the first thing we want to define is a perpendicular bisector. And a perpendicular bisector is a line at the midpoint of a line segment perpendicular to that line segment. So here, for example, is a perpendicular bisector. We can see that it cuts this line segment in half so that these two new line segments are the same length. And of course, it's perpendicular to the original line segment. The other thing we need to remember is the definition for the chord of a circle. That's C-H-O-R-D, chord. The chord of a circle is the line segment interior to a circle that connects at any 2 points. So for example, this is a chord, this is a chord, this is a chord. These are all chords. And of course, the diameter of a circle is also a chord, but it has a special name, diameter, because it passes exactly through the center. And I'm not going to prove it here, but it's easy to do on your own. An important lemma or tool that we're going to use in our proof is that the perpendicular bisector of any chord passes through the center of the circle. So let me put a chord on this circle. Oops. There we go. Oops, not exactly. Sorry, I'm not the best at drawing diagrams by hand. And we can just eyeball it and get pretty close. Perpendicular bisector of this is going to be like about right there. And that passes through the center of the circle, which is, just eyeballing it about right here. So that's true for any chord. The perpendicular bisector of a chord passes through the center of the circle. So I'm going to go ahead and write that here. Oops. Lemma. Okay, so now we're ready to do the proof. I'm going to shrink down this triangle so we have enough room. Not let me do it. Here, we'll just do it this way. Nope. Okay, let's just shrink that down a little bit. And I'm going to start by drawing the parallels of the sides. Let's label our sides again, A, B, C. So the parallels are the lines that are parallel to one side that pass through the opposite vertex. So, for example, oops, to duplicate that, this would be one of the parallels. This would be the parallel of side AB. No. This would be the parallel of side CB. And this would be the parallel of side AC. Okay, great. And if we look at this parallelogram formed by the triangle itself and the parallel, so let me highlight this parallelogram. Let's look at this one. We know that a parallelogram, the opposite sides are the same length. So if this side of the triangle here has length lowercase b, we'll call this one lowercase a and this one lowercase c, we know that this side of the parallelogram has length lowercase b. Similarly, you can say this one has length c, this one has length a over here, and if you keep working this out, you'll find that this one also has length a, this one has length c, and this one has length b. Now this is getting a little messy, so I'm just going to indicate it with marks. So AB will have 1 mark, and this will also have 1 mark, CB. So we see that the triangle formed by the parallels has twice the side length of the original triangle. Okay, I'm going to go ahead and shrink this down a bit again, and I'm going to get rid of this highlighter. And now what we want to do is we want to draw the circle through these 3 points. So we know that any circle can always be defined by 3 points, and I'll just give it a really rough go. Oops, that's a hexagon. That's a circle. And let me get it so that it passes through all 3 of these points. It's going to be a little tough. It needs to be maybe a little bit bigger. There we go. That's pretty close. What we're going to do is we're going to draw the perpendicular bisectors of these chords formed by the larger triangle. So the perpendicular bisector here is going to be perpendicular to this line, and just doing my best by eyeballing it. maybe a little more this way. That looks pretty good right there. And just extend it. And then we're going to draw the perpendicular bisector of the chord next to vertex A. So that looks pretty perpendicular. Let's just move it to the right place and extend it. And then we're going to draw the perpendicular bisector for this chord. Do that one in red. Should be like a perfectly vertical line. That looks pretty good right there. And then we will also extend that one. It's pretty close. My drawing's just a little bit off. I think maybe this one is not perfect. And we'll need to adjust this one here. We will delete this one, and we'll just extend to this line. Nope, not that one. There we go. So because these are perpendicular bisectors of the chord, and because the outer triangle has twice the side length of the inner triangle, we know that these points right here are at the midpoint, so they pass through the line. Moreover, because this side of the larger triangle is parallel to this side of the smaller triangle, and because this right here is a right angle, we know that this is also a right angle. So we know that this red line is perpendicular to the smaller side of the triangle. Same is true for the blue line, the green line and the blue line. And we see that all three of these intersect at a single point. This is called a construction, by the way, this method. And we've shown that by construction, the heights of the triangle have to intersect at a single point. And we know these are the heights because they're perpendicular to one side and pass through the opposite vertex. So just a few more notes. First of all, we've been looking at acute triangles where all of the angles of the triangle are acute. And you'll see that the orthocenter will always be inside the triangle. 1, roughly. 2, roughly. 3. So it's always going to be inside the triangle. If we have a right triangle, I'm going to use the highlighter here because the line that's perpendicular to this side on the bottom here that passes through the opposite vertex is just the side of the triangle. Same for this height here. It's just the side of the triangle. And for the third height, it's going to pass through that vertex and it's going to be perpendicular to this side. So we see that the orthocenter, or the intersection of the three heights, is located at the vertex that is opposite of the hypotenuse, and that's true for all right triangles. Finally, if we have an obtuse triangle, which has one obtuse angle, let's do a nice big angle like that. Maybe even make it a little bigger. And I'm going to align this to the base just to make it a little easier for me to draw the heights. That looks pretty good. Okay, so we have one height here. We have one height that goes maybe like this. and we have one height that goes maybe like this. And now if we extend this height here, we can see that the orthocenter is always outside of the triangle. So for all obtuse triangles, the orthocenter, or the intersection of the three heights, is going to be outside the triangle. For a right triangle, it's going to be on the vertex opposite the hypotenuse, and for an acute triangle, it's going to be interior to the triangle. So that completes the two proofs: the geometric method by construction and the algebraic method by writing the equations of the line.